This is part 2 where we will study virtual memory mapping. Well, before going to the virtual memory mapping, let's have a look about what is virtual memory and the virtual address and the physical memory and the physical address. Let's take a leisure. Well, the virtual memory is the program's memory. That means where the MIPS use. While the physical memory is the RAM that is installed with your computer, right? Now, to handle the virtual memory, depend on your virtual memory size, you need to have some bit of address, and that address is known as physical address, while the virtual address is fixed for the MIPS and it promised 32-bit address, and that's supposed to be the 4 GB or 2 to the power 32 minus 1. I'd like to clear this thing again. So the virtual address or the virtual memory is the memory that use your program. That means your MIPS program use, and the address supposed to be 32-bit. That means 4 GB. For example, these are the virtual memory, and to address this virtual memory, you need to have 32-bit address from 0 to this. This is known as virtual address. On the other hand, depending on your RAM size, you have physical memory, and to explain the physical memory, you have different address size, right? For example, if you have 2 GB of memory, you have the 31-bit address here. So we can map directly with your virtual address to the physical address, and if you don't have, we need to go to the disk for this. This is the basics for memory mapping, virtual address mapping. So now we're gonna discuss about how the pages are mapped, how the physical address and the virtual address are mapped, right? Well, this is your CPU register file. Think about a different way, the same as like the cache when we studied at the cache mapping. So we have a table that maps the virtual address with the physical address, and this is physical address from where the CPU can load the data register file, right? So let's execute the first instruction, load R3 1024 R0. That means the virtual address is 1024. So in your page map table, this virtual address must be here, and the corresponding physical address is written here. So your virtual address is 1424 is here, and the corresponding physical address is 6. So you go to the physical memory address 6 position, and you got data for the register R3. Again, for the next instruction is the physical address you need to find out to read the data from here. So the virtual address is 512. The corresponding physical address is written here, and the physical address you're gonna find from here, and the data is come here. Another example for here is another address 800, and this is read that this is not here. So this page says that this address is not available in the physical memory. You need to put up the disk. So how do we understand this? Well, this is not in the memory. So if this is not mapped, and then this remaining part is handled by the operating system. So it's gonna look for the hard disk and then find the address in the hard disk, and after finding the operating system load it into the physical address and update the page table accordingly. So the data for R4 is loaded in the 4 position of the physical memory, and the operating system then update the page table with the 4. So now The CPU can say that, oh, okay, the address is 4, so it's 4 is come here to load this. This is the way that we can work with the page mapping. So physical address and the virtual address are mapped, right? So it's okay, but what are the problem? So if you think about the virtual address physical address mapping, each address having 32-bit and the physical address depends on the RAM size. For example, it's a 2 GB RAM, then it's 32-bit. So it's a big disadvantage to handle such a big data like we are studied. Also in the cache is a huge amount of data. So what we can solve it, we can solve it with the page. How can we do this? That we can say that it's a page table. So this data is somewhere, all the address in 0 to 4095 is located anywhere in the physical address in 4906 to 8891. So the thing is that this physical page, this virtual page are mapped with this range of this physical address. So we can reduce the size from this. Now the problem is, okay, we know this address is somewhere between these, but how we can know which particular location? For example, here is an example. So these are the page. These are the pages of the page range for the virtual address. And here is the mapping, like this. Well, so in a particular page, in virtual address and the physical address, these are same. So within the range, we need to find out which particular part of the virtual address is the physical address. So we use the offset. As this block size is same in virtual address and the physical address, the offset will say the which particular part is of the virtual memory is the actually in the physical address. So we get the page offset. By page offset we will get the decision. So here is an example. So you have a 20-bit of the page number and 12-bit of the offset, right? Well, so how can we find out this? The first thing is the 20-bit page number is come here and says, hey, I want to search this page number. For example, this is 000, and we'll got the physical address, and the physical address is come here, page number, and the offset is the same. So you got the address like this. So this is called the translation. Here is an example. So this is your address. Okay. So the last three digit is a 12-bit is the page offset. So it comes here. The remaining part is gonna the page number. So once you look the page number in the page table, you got the page number. Physical address. Physical page number, right? The physical page number come here and the offset is same to come here, so you're gonna get the address from this. This is the way that you're gonna find this address. Thank you very much.